Okay, so this is part two of the graphs lecture, and today we're going to talk about the shortest path algorithm. So the problem is, given a directed network, so a directed graph, find a path from one vertex v to another w, such that the sum of all weights is as small as possible. And that's an important problem because we want to find the cheapest cost to get from a source to a destination. A lot of things like airline routing. Traveling in your car, you want to find the cheapest route to get somewhere. So it turns out it's just as easy to, given the directed graph in which each edge has a non-negative weight or cost, find a path of least total weight from a given vertex called the source to all the other vertices in the graph. So if you're going to find one, it's just as easy to find them all. And this problem is often called the single source shortest path problems because you're going from a single source. To solve this problem, we'll just use a greedy technique that's often known as dijkstras algorithm. And here on this slide, it's going to be very important for you to discern the difference between Edgar Dijkstra and greedy Smurf. That'll come up again and again in computer science. It was Dijkstra's shortest path algorithm that did it, but it's a greedy approach. And of course, greedy algorithms were developed by greedy Smurf. So the algorithm works by maintaining a set S of distinguished vertices whose shortest distance from the source is already known. Initially, we only know the source. We know how to get where we're at. And at each step, we add to S a remaining vertex V whose distance from the source is as short as possible. Assuming that we have non-negative cost, we can always find the shortest path from the source V that passes only through the vertices in S. And we call that method special. So at each step of the algorithm, we use an array D to record the length of the shortest special path to each vertex. Once S includes all the vertices, all the paths are special, so D will hold the shortest distance from the source to each vertex. So this is the code from Aho, Hopcroft, and Ullman. This is the one that I learned a long time ago. Cruz and Reba have a bit more of a weighty implementation, and we'll cover Malik's as well. So we begin initially S, the set of distinguished vertices is 1. For 2 to n, add to the vertex the one that has the minimum weight. So from 1, the next one we would add is 2. And then that would update things so that we know that it had a distance of 10 to get to 2. Would still be the distance of 100 to get to 5, a distance of 30 to get to 4, and a distance of a total of 60 to get to 3. So here we start out with 1. We add 2 into the distinguished vertices. Initially, when we're at 1, the distance to 2 is 10. Distance from 3, as far as we know, we can't reach there. Distance to 4 is 30, and distance to 5 is 100. So we take the minimum of those, 2, and add 2 into the distinguished vertices. Now, for 2, we know there's a distance of 10. For 3, our distance is now 60, because we go through 2, we can get to 3 with a distance of 50 more. So that's a total of 60. For 4, it's still 30, and for 5, as far as we know, it's still 100. So which one of those is the smallest? It's 4. So we add 4 to our set of distinguished vertices, and then that updates things so that we know the distance from D2 is still 10. Distance to D4 is now set at 30. Can we get to 5, or can we get to 3 any cheaper? No, that's going to be 30 plus 20. That's going to be 50. So that's a shorter path to 3. And the distance to 5 is now going to be 30 plus 60. That's 90. Okay, so which one of those is of the remaining ones is the shortest? That's 3 with a cost of 50. So we now add 3 to our set of distinguished vertices. It's 10, 50, 30. But when we go through 3, from 1 to 4 to 3, that's 50, and we can add 10 more to get to 5, which is 60, and we now found the shortest path to get from 1 to 5. So, initially we might be tempted to go directly there, but that would cost us 100. Maybe there's some extra tolls on the route, or it's a premium airline route. But if we go through 4 and then 3, we can get to 5 a little bit cheaper. And sometimes you find that with ghost cities on airlines. So it always pays to do the shortest path algorithm. It works because, in the words of Gordon Gekko, greed is good. What appears to be locally the best thing to do turns out to be the best overall. And find the distance to the vertex W that's outside of S, but has the special shortest path is what we're doing. So it also works because imagine that we have X, and we know that the shortest path to V is from 0 to V. Well, if X was actually shorter, then it would be in that set colored in orange, which are the distinguished vertices, if it was actually shorter to get to X. So um, just based on the fact that X lies outside of there, we know that it's not on the shortest path. So the running time, the main loop gets executed n-1 times, where n is the number of vertices. And there are two loops in main. Each one is executed n-1 times. So those are nested loops. So they contribute n-1 squared operations. And the work done outside the loops is O of n. So the total running time is the max of those, which is O of n squared. So Malik's version is a little bit more complicated. We need to keep track of the weight of the edge, the weighted graph, the weight of the path, and the source. The shortest path is the path with the smallest weight, and the shortest path algorithm, called the greedy algorithm, which was developed by Dijkstra, is given below. Basically, we have the weights, and the weights are set up so that there's an edge in G, and WIG is the weight of the edge between the two of them, and infinity if there's no edge from VI to VJ, and that's the setup. Then we initialize the array smallest weight, so the smallest weight is the weights of the vertices of the paths from the initial vertex to any other vertex to which it's connected. And the smallest weight from the vertex to itself is 0. Find the vertex V that's closest to the vertex for which the shortest path has not been determined, mark it as the next, and then update the weights now that we're allowed to go through W. And we repeat these steps 3 through 5 n-1 times. So let's take a look at how it works. Here's a network diagram with weights attached to the different paths. So we start out at 0, and where can we get to from 0? Well, we can get to 0 itself for a cost of 0. We can get to 3 for a cost of 2. We can get to 4 for a cost of 3. And we can get to 1 for a cost of 16. As far as we know, we cannot get to 2. So here's what our graph would look like. From 0 to 1, it's 16. From 0 to 2, we can't get there as far as we know yet. From 0 to 3, the weight is 2. And from 0 to 4, the weight is 3. So which one do we add in? The one with the minimum. So we would add in 3 to our set of distinguished vertices. And that's where the weight found in the bottom is set. So we would have 3 added in there. Now we update things. To get from 0 to 1, we can now go through vertex 3, which is 2 plus 12, that's 14. So it's actually cheaper to get to 1 than going there directly, going through that route. We still can't get to 2, and our cost to get to 4 is 3. So we're going to add in 4 into our set of distinguished vertices. Now we update the weights. We can actually get to 1 for 13, and lo and behold, we can now actually get to 2 for a cost of 7. So of the ones that are left, we would add in 2. And then last but not least, we would update that path to number 1, which would go through 0, 4, and then 2, which would give us a total cost of 10. And that would add in our shortest path. So the shortest path between any of these vertices between 0 and 1, it's 10. If we go 0, 4, 2, 1, to get to number 2, it's just a simple, it's going through 4 and then get to 2. to get to number 3, it's just go directly to number 3 with a weight of 2, and to go to number 4, it's just cheapest to go directly from 0 to 4 for a cost of 3. And that wraps it up. Work through a couple of these examples. They're worth doing and worth knowing how to do the shortest path algorithm. It's a very common algorithm in computer science, and you'll be using it a lot. Thanks for listening.